So in our last lecture, we introduced this concept of an integral of this form, where f is a vector valued function, and c is some sort of curve in R3, right? Possibly in R3. So we're trying to understand this f dot dr. We call this a line integral, or it's also sometimes called a path integral. Okay, so one way in which you can think about this in XYZ space is that, well, f in XYZ space can be given in that form. It has components f1, f2, and f3, and dr in general, it's got something which is in that form. And once you have that in that form, what you can do is when you take the dot product, you're going to get these sorts of things. And one thing which we discussed in the lecture last time was that even though I can split this up into 3 different integrals, I can't do each of these integrals individually for general curve C, because, for example, when I'm trying to do this, I want to look at what happens when x is changing. But when x is changing and I'm continuing to remain on the curve, the other variables are changing as well. So y is changing with respect to x and z is changing with respect to x. So what I need to do is some sort of complicated dependence of x over there, which I can't necessarily find. So that's kind of hard. And last time we did this, we used this in very specific situation where our curve just went along the coordinate axes, and you could sort of get rid of a couple of the other integrals as you went through this. But what I want to do now is to try to think about how we can do this in general, right? So we've got a general curve. We've got a general curve C in space, and I'm trying to do this integral here, right? So the idea here is that you want to try to convert this to an integral with one variable, just one variable, because if not, this is kind of complicated. There's x's and there's y's and there's z's, and then there's complicated dependence over here. It's not really easy for me to figure out what to do. I want to convert it into one variable, and the variable that I'm going to convert it to is, let me call the variable t, because the point is I'm coming along a curve, right? I'm just moving along a curve. So if it is possible for me to identify my location along the curve with respect to just one object, t, okay, then at each different value of t, this integrand is going to take different values, and then I just want to add everything together. So I want to somehow try to convert this to an integral with just one variable, right? So what I'm going to do is this idea here: represent the curve's general points in terms of one quantity t. And this process is called parametrizing the curve, finding a parameter for the curve. So for example, the beginning point of the curve, I might identify as t equals 0. Then t is different over here, it's different over here, it's different over here. And then this last point might be t equals 2, right? I don't know, these values I just made up. They can be just any old values, but a general point is going to have a t value which is in between these two endpoints, and that gives me my location. So this r, the general location of this, is a function of t, and I think of this t as a parameter. So I'm just moving along this curve. It tells me how I'm moving along this curve. So a simple way, I mean, t could be, for example, the length along the curve, right? So I start at 0. This might be 1 unit along the curve, and so on and so forth. That might be my parametrization. We'll get to that later in a lecture later on. But in general, it can be just any parametrization. And it turns out that the parametrization is not unique. There are many different ways in which you can parametrize a curve. So it doesn't, as long as you can parametrize it, that's all that matters insofar as doing the integral, right? So now, how do we do this, right? So if you can parametrize a curve, I claim we can write down these integrals, right? So the integral that I'm trying to do is this sort of integral. I can write down everything purely in terms of t, just a single variable integral, that the sort of thing that we're quite familiar with from Maths 1. Okay, let's develop this via an example. Let's try to find the work done by the force. So here's a force field. It depends on x, y, and z. When taking a mass along the straight line from 0, 0, 0 to 1, 2, 3. Right, so it's a straight line in this case that I'm looking at. I have the point 0, 0, 0 to 1, 0, 3. F is going to change depending on my location on the line, and I want to find f dot dr in this case. So I'm going to follow the idea that I had earlier. I'm just going to think of different t values along this and try to write everything related to this integral in terms of t and dt, right? That's the whole idea. So the first thing that I'm going to do is I'm going to write down the general parameterization of the curve. Now, this should be something that you've seen before, because I'm going to start at this point and I'm going to end at that point, and I'm going to let t go from 0 to 1. So here's my beginning point, and then I'm going to add t times the difference between the endpoint and the beginning point, right? So this here is a vector which is just exactly that vector, right? So if I go, if t is equal to 1, I'm going that distance from this original point, so I end up at the final point. So if t is equal to 1, I'm at the final point. If t is equal to 0, I'm at the initial point. And if t is sort of equal to a half, let's say, I'm halfway in between. Yeah. So this is a very standard way of parametrizing a curve. So this point is t equals 0, this point is t equals 1. This is standard parametrization of a line segment. So this is good, right? So let me just sort of simplify this a bit. So what do I get? So this vector here is just a vector 1, 2, 3. And then I have 0 plus t times the vector 1, 2, 3. Yeah, so I can write this now as, so I've written it up here in component form, but let me write it down here in ijk form, because these are completely equivalent forms. So the I component is 0 plus t times 1. So it's just going to be a t. The j component is 0 plus t times 2, 2t, and then finally 3t. Right? So my general location r of t, I can write in this form. And a way of thinking about this is, of course, this is my x coordinate. So x is changing with respect to t, and that function is t. Y is also changing with respect to t, and that function is 2t. And similarly, z of t is equal to 3t. Okay, so now I've got everything. I've got at least my r. I've got this expressed in terms of t. But I'm trying to calculate f dot dr. So I need to figure out what f is as well, right? So here's what I have for r. Now let me try to figure out what f is. Well, f at a general location is given by that. So a general location x, y, z is given by that, which means that f at a general location x of t, y of t, z of t is given by this. So I have a z in the x component, I have an x in the y component, and I have a y in the z component. But the point is that now we know what x of t, y of t, and z of t are. There are these things over here as t is varying. So instead of z of t, I'm going to put in a 3t. So instead of x of t, it becomes a t, and y of t, it becomes a 2t. So this is great. So now I've got my r of t purely in terms of t, and I've got this f that I'm trying to calculate purely in terms of t. As t is varying along the curve, at each point along the curve, I can just plug in the value into this function. When t is equal to 0 at the beginning point of the curve, well, I just plug in t equals 0. When t is 1 at the end point, I plug in t equals 1, and so on, right? So I can figure out what the force is at any general point along the curve. But what am I trying to do? I'm trying to find f dot dr. So f at a general point r dot dr, right? What am I'm trying to write this in terms of t, right? So this r, I'm writing it in terms of t, and I've already achieved that. I know what to do, right? But wait a minute, I've got this dot dr. Yeah, that's not good. I want to write everything in terms of t, and so I want to have a dt here, and I want to put in 0 to 1 because I know that those are my limits, because t equals 0 is the beginning point and t equals 1 is the end point, the way that I've chosen to parameterize this curve. So I really do want to have a dt there. Right, so I want to go from here to here and have a dt. How can I do that? Well, you can do a very clever little thing. So you write this here, right? You dot it with dr by dt times dt. So this is a perfectly standard thing that I've done here. It comes from single variable calculus because t is our only variable here in many ways, right? So yeah, there's a dot product and so on and so forth, but it doesn't really matter. So basically what we're doing is the equality of this. So this dr, right, which is the change in the of r, if you will, the change of r, I can write it as the rate of change of r with respect to t times the change of t. Right? So that's all that I'm doing here. Now I'm in business, right? I've got my dt over here, and indeed I can go ahead and put the 0 to 1 now because it's actually meaningful, remember, because this integral sign has to go with that differential element based on what you said. So I can put in 0 to 1 over here. So now I'm reduced to trying to find these two things. This I've already found. Do I know this? Let's see. Yeah? I know that r of t is equal to t I plus 2tj plus 3tk. So if I want dr by dt, I just differentiate it with respect to t, right? So dr by dt, which I can also call r prime of t, or you probably are more used to saying r dash of t. So r prime of t is the derivative of this with respect to t. So what happens? It's a derivative of a vector with respect to t, but it doesn't really matter because these unit vectors are actually constants. They're not functions of t. So if I differentiate t times I with respect to t, I just get this constant, which is just a vector. I differentiate this with respect to t, I get 2j. Differentiate that with respect to t, I get 3k. So dr by dt is itself a vector, yeah, which is fine. Right? It's not a big deal. That's a vector. And down here, I've written down something that we calculated in the previous page. We know what f is as well. So I know what that is. and I know what that is. So now it's just a simple question of plugging it in. Notice that there's also a dot product over there. Okay, so here are the steps that I'd written up to this point. So now I'm just going to plug it in, right? So here's my f, and here's my dr by dt. That's I plus 2j plus k. My f is given like that, and I've got a dot product here. And now the vectors go away, right? When I take the dot product, I'm going to get 3t times 1 plus t times 2 plus 2t times 1. This is what I get, 3t plus 2t plus 6t, right? So if you add those together, there's 11t. But the point here is that when I come to this point, I'm just down to a maths 1 integral, right? It's just a single variable. There's no vectors, no evidence of any vectors. All the vector field issues are gone. The fact that this is some curve in three-dimensional space is all gone. It's just down to a single variable, straightforward scalar integral, right? So you can just go ahead and do the integral. It's 11t squared over 2. It's 1102. Okay, so that's our answer in that case. Okay, so the lesson here, if you will, is when you're doing these integrals, you're doing an integral like this, the whole idea is that you must parametrize the curve. Write the curve so that there's a parameter, let's call it t, which is varying along the curve. You set up the parametrization, and then you write this dr as dr by dt times dt, and then you just do this. You figure out what f is at a general location, and you've already figured out what the general location r of t is. So you differentiate that. You put in the appropriate limits. In the previous case, our limits were 0 to 1, the way that we parameterized it. But the whole point is that this whole thing just collapses to a single variable integral, and the vectors go away as well, because after you take the dot product, it's gone. Right? So then it's just a function of t dt. Right, so that's all it is. Okay, so now in order to do this, the big trick here is, can I parameterize any given curve? And that's the issue. If I give you a really complicated curve, it's actually quite hard to parameterize, or I have to tell you how to parameterize it. So it's hard for you to figure this out by yourself. But there are a couple of fairly straightforward parameterizations which you should know and have at your disposal to be used very quickly. One of them is a straight line from a point A to B, and this is exactly what we used, in fact. Right, so it's given by this over here. So the original point plus t times, well, the displacement vector all the way up to the final point, and then t goes from 0 to 1. When t is 0, you're at A, t is 1, you're at B. Right, so here's another sort of parameterization. Now this is a circle of radius A in the xy plane centered at the origin. So you might remember that if you have a circle like this centered at the origin, the x coordinate is a cosine theta and the y coordinate is a sine theta, and as theta varies, you go all the way around, right? So theta equals 0 all the way around to 2 pi. So theta going from 0 to 2 pi. So here I'm using theta as my variable of parameterization. It doesn't really matter. You can use just any old variable that you want. And in this case, my limits would be 0 to 2 pi. Here my limits are 0 to 1, right? Parameterizations are not unique. There might be other ways of doing it. It doesn't really matter. You'll always get the same answer in the end, because physically you're doing exactly the same calculation, f dot dr. Okay. Now, just a few other comments. If C is a simple curve, by simple I mean non-self-intersecting. It doesn't go back on itself. It's a curve which is like that. And in that case, my r of t, which is my parameterization, right? So from values on the t-axis. So it could be from t equals 0 to 1, for example, as it was in the example that we did, or it could be from t equals 0 to 2 pi. All right, so if you're using a parameterization for a circle and so on and so forth. Okay, so you got this function here. Given a t value, you're finding a location in three-dimensional space. There's an x, a y, and a z. Okay, so C could be simple. It could be something like that, but C could be self-intersecting. So self-intersecting is a curve which is not simple. So the word simple means it doesn't intersect. So you could also have a curve which does this, and it comes back and it intersects on itself and does that. Well, you can still evaluate an f dot dr along this, because the curve actually still does make sense, right? So I just want to establish a little connection with something we talked about last time. So when you parameterize a curve like this, right? So you're coming up with a function r of t from this t-axis to locations over here. So that's what you're coming up with. So let's just look at a possible example. So that point might be t equals 1. Over there, your t equals, 0, 1. And let's suppose this is t equals 2, this point of intersection, then 3, then 4. And then when you come back again here, you have to be beyond 4, right? So maybe that's t equals 5 again. We're talking about exactly the same point though. Right, but it doesn't really matter. There's a nice continuous variation. As t is varying, I'm tracing this out in space. Yes, I'm intersecting, but it doesn't really matter. Everything is quite clear as I proceed, and t equals 6 might be over there. But what I observe here is that in this mapping, right, t equals 2 maps to that point, t equals 5 maps to that point. So this means that the mapping here is not an injective mapping in this case. There are 2 points which map to the same value. Not a big deal, right? In this case, we are not insisting that this be a bijection, right? So in situations like this as well, we are perfectly allowed to do integrals f dot dr as well. Okay. One little sort of conceptual understanding here is that r prime of t is going to be a tangent vector to the curve. Yeah. So r of t is a parametrization of a curve. Yeah, as t is varying, I'm going along the curve like that. So here's a parametrization. If you take the derivative of that, it turns out that that is a tangent vector to the curve. Why is that true? Right, that's kind of weird. Why is it true? Let's think of this in this sense, right? So suppose I am at point r of t. Let me suppose I increment t by a small amount, delta t. So I look at then r of t plus delta t. Well, I'm still on the curve, of course, because my function r ensures that I'm on the curve, but I'm thinking of delta t as small, so I'm fairly close to my original point. And that means that if when I take the difference between these two vectors, that's actually this vector here. Right, when difference between these two locations, that's going to be that vector. Okay, so this pink vector is that vector, right? So this is essentially I'm going to think of this as dr. It's sort of like a delta r. It's a change in r, if you will, but I'm thinking of this in an infinitesimal sense. So I can sort of think of this as dr. Now, you might remember this. If I write down the derivative r prime of t, well, it's going to be r of t plus delta t minus r of t over delta t, and then I take the limit as delta t goes to 0, right? So that's how I take this limit, and that gives me r prime of t. Well, what I've just argued here is that this pink vector here is exactly what I have up here. Okay, so what I have up here is this vector which represents the change in r, and that represents a vector which is like this, right? Going from a point on the curve to a very close nearby point on the curve. Now, as delta t gets smaller and smaller, this point gets closer and closer to this. But the point is that this vector continues to remain essentially on the curve, more or less on the curve. So it becomes increasingly tangential. Right, so as you get closer and closer, it becomes increasingly tangential, if you will. Right, so this is exactly the concept of the secant line getting closer and closer to the tangent line, something that you learned back in high school as well. Right, so over here, this line connects together 2 points which lie on the curve. As you push this point closer and closer, the line connecting them gets closer and closer to a tangent line. Yeah, so this gets closer and closer to a tangent line, that gets closer and closer to a tangent line. This has no direction, it's just a value, which means that this thing here has to be a tangent vector to the curve. So that's just a little observation. This r prime of t that we get when we're doing these integrals, right, which sort of pops out. This guy here, r prime of t, which, when we're doing this integral, this is related to a tangent vector at a general location. So you got a function dotted into a tangent vector, and that tells you essentially you're looking for the component of the function in the tangential direction, right? Which actually makes sense from our discussions earlier on about a force, right? So that's what it ends up being. Okay, so we'll stop here. So next time we're going to talk about a slightly different type of line integral. So it turns out that you can define something slightly different. This is one type of line integral based on a vector field, but we can define a line integral which is based on a scalar field, the variation of a scalar field along a general curve as well. Next time.